Hello everyone and welcome to TLE Eliminators for CodeChef Starters 212. We'll be discussing problems 1 to 5 of Division 2 today. So, Div 2, right? We'll start with problem 1 and go all the way to problem 5. How was the contest, guys? How many problems solved? How do you all do? 3, 5, okay, cool. Yes, we're just starting. Alright, so we'll be discussing all the problems one by one. Looks like most people could do around 3 problems, which is cool. I did 5 problems today, so we'll be discussing the first 5. Anyways, okay, so the first problem, pretty simple, so we won't spend too much time. So, exit door. There are n people sitting inside a single row in a movie theater. Each person has assigned a number from 1 to n. So, basically, their numbers are a permutation from 1 to n. After the movie ends, people start leaving the hall one by one in order of a decreasing number. That is, the person with the highest number leaves first, then the second highest, and so on. When a person leaves, they can go either left or right out of the row. Now they will choose the direction which minimizes the number of people they disturb. Now you have to count the total number of people disturbed. All right. So let's just take this example of 1, 5, 3, 4, 2, and we understand the problem better. So example, and we have 1, 5, 3, 4, 2, right? So these are the people sitting in the row, and we know that the highest numbered person, so 5 in this case, is going to be the first one to get out, right? The 5 is the first one to get out. So he has two options, either get out this direction or get out this direction. Here he disturbs one person, here he disturbs three persons. So he will choose the minimum one, which is this way, right? He'll disturb one person only. So we can add that to our answer. Our answer will be equal to 1 plus. Now, who is the second person to get out? 4 is the second person to get out. Now, if he goes this way, he'll disturb two people. And if he goes this way, he'll disturb one person. So again, he'll choose the one with the smaller answer. So plus 1. Now 3 needs to get out. He can get out either way because one person on the left, one person on the right, he will disturb. So 1, and then the remaining 2 will do 0. So the final answer is 3. Yeah, so the answer for this test case is 3. So basically, what we can observe is for each person, uh, for each person, for each a of I, we choose a direction. We choose a direction such that uh, the number of elements a of j less than a of I is minimized. Right? So this is basically what we're looking for. Does that make sense? Right? So Fenwick on second question, no, I don't think there were any data structures used much in this contest. Okay, so basically our answer is going to be for each I. So our final answer, we can just write it down directly. So our answer is going to be sum for each I, minimum of a of j less than a of I for j less than I, comma, a of j less than a of I for j greater than I, right? And that's it. And then when we find this sum, we can print our answer. They will choose the minimum direction, and we are finding how many they will disturb on either side for each element, right? So that's it. And if we implement this naively, it will be in big O of n squared. But as you can see, n goes up to 10 over here. N goes up to 10. So this code will pass, right? N goes up to 10. So at most we will get 100 times 10 power 5 right? 100 times 10 power 5 over all the test cases. So n less than equal to 10, number of test cases less than 10 power 5. So at most we will have 10 square times 10 power 5 operations, which is perfectly all right. Yeah. So big O of n square solution will pass, right? Direct big O of n square solution. Cool. So yeah, let's just have a look at the code for this. Okay. So we can define our answer variable as 0, and x is going to be how many are less than it to the left, y is going to be how many are less than it to the right. This is we are doing for each a of I. Then we're simply just counting to the left how many are less than it, to the right how many are less than it. We add the minimum of those to the answer. We do this for all the elements, and finally we print the final answer, right? And that's it for problem 1. Pretty straightforward problem, I would say, right? Yeah, pretty straightforward problem. Any doubts? I wrote n log n code for this because I didn't see constraints. Yeah, makes sense. If you do it with, I think, ordered set or something like that, you can do it in n log n, or some clever use of sets. You can do this in n log n, but yeah, the constraints allow n squared. And obviously, the easiest and fastest way to do this would be n squared, right? Uh, uh, yeah. Okay. So now let's move on to problem B. And what is the problem B? Binary flip. Okay. Binary flip. Okay. So you're given a binary string s of length n. Let count 0 0 equal to the number of substrings 0 0 in s. Let count 1 1 equal to the number of substrings 1 1 in s. In one flip, we can choose any index I and toggle s of I. So 0 will become 1 and 1 will become 0. Your task is to determine how many flips will make count 1 1 greater than equal to count 0 0. Okay. So that's all we need to do. We need to determine how many flips taken to make count 1 1 greater than count 0 0. So the number of substrings which are equal to 0 0 should be less than equal to number of substrings equal to 1 1. And basically we can do toggle operation, right? Okay. And n goes up to 10 power 5. So the expected time complexity is big O of n, or big O of n log n. Okay. So expected time complexity big O of n, or big O of n log n. Okay. So basically in one flip, since we're able to flip from 0 to 1 or 1 to 0, right? Given operation, flip from 0 to 1, or we can flip a 1 to 0, right? 0. But our goal is to increase the number of number of 1 1s, right? If there are not enough 1 1s, we want to make more 1 1s. That's our goal. So basically we will never do the second type of operation. We will never do this, because this is always hurting our answer, right? We will only do the first type of operation. We will only do this because there's no sense to flip from 1 to 0, because we want to increase the number of 1 1s. So we will always flip from 0 to 1. Okay. Now we're going to prove our next idea, and our next idea is basically going to be, if we have some string such that the number of 0 zeros is greater than 1 1s in this string. If the number of 0 zeros is greater than the number of 1 1s in this string, then in one flip, how much can we change this value, right? So if count of 0 0 is currently greater than the count of 1 1, then by how much can we change this value? Like how much can we bring count of 1 1 up, and how much can we bring count of 0 0 down, right? So okay, let's see what happens if we take a bit and flip it. Right, if we take the 0 and flip it, what happens? So what we can say is, if we flip this, we have a new 1 1, right? We have a new 1 1. Also we have a less 0 0, right? 1 0 0 vanished and one new 1 1 came in, right? So basically what essentially happened was, count 0 0 increased by 1, right? Count 0 0 decreased by 1, and count 1 1 increased by 1, right? So the difference, count 0 0 minus count 1 1, the delta of this difference was -2, right? Basically we decreased 1 0 0 and we increased 1 1 1. So basically we became 2 steps closer to our goal, right? We came 2 steps closer to our goal. Our goal is count 1 1 greater than equal to count 0 0. We can rewrite this as, count 1 1 minus count 0 0 should be greater than equal to 0. So if it was less than 0, basically what we have done by flipping this one bit, right? By flipping this bit, what we have done is, we have added +2 to this, right? We have basically added +2 to this. So we're basically +2 closer to our goal. Okay. What if we flipped some bit over here? Okay, what if we flipped some bit over here? If we have 3 zeros in a row, and we flip the middle bit, then as you can see, we lost 1 0 0 and we lost another 0 0 here as well, right? So again, this quantity has decreased by 2. The count 0 0 decreases by 2. So we can say that again, our answer has become plus equal to 2, right? Our answer has become plus equal to 2. So um, basically, if we have 0 0 0, then flipping the middle 0, converts it to 0 1 0, which will increase our count 1 minus count 2 by this increases our count 1 1 minus count 0 0 by 2, right? So each time we're able to increase our count 1 1 minus count 0 0 by 2. And also if we had a pattern like this, 0 0 1, again flipping the middle one, increases the count by 2, right? So basically at each step, at each possible step, if we can flip a 0 such that this quantity, count 1 1 minus count 0 0, increases by 2, right? This quantity increases by 2. So basically, if this was true, right? If this was true, then at each step what we can do is add +2 and add +2 and add +2 until this becomes greater than equal to 0. Okay, so I hope you understand. At each step we can do a +2 operation, because the two cases 0 0 0 as well as 0 0 1, right? So if there's a 0 0 in the string or in the values, then always we can flip a bit in such a way that the answer increases by 2, or this invariant increases by 2, or the desired quantity increases by 2, right? And as long as it's less than 0, we can keep adding 2 until it becomes greater than equal to 0, right? And I hope you understand that if the number of zeros is greater than the number of ones, like if the number of 0 0 is greater than the number of ones, then definitely we'll have either this pattern or this pattern. And also by flipping a single bit, we cannot change more than 2. So always we are doing the maximum change possible, which is a +2 change, right? So I hope that is clear. Yeah. Zero 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 is 2 pairs. Arav, the 0 0 0 is 2 pairs, okay? Because we're counting overlapping pairs. At any position I and I plus 1, which is equal, is a substring, right? So all possible substrings of 0 0 have to be counted. So that will make it 2 pairs. I hope that's okay. So what is our final solution? Our final solution So it's going to be just basic maths, right? Since we can increase this quantity by +2 each time, if count 1 1 minus count 0 0 is greater than equal to 0, answer is equal to 0. Else, answer is equal to ceiling of uh, count 0 0 minus count 1 1 divided by 2, right? Why? Because each time we're increasing by 2, so that's why the required quantity to increase is, let's say, this much. So we need x by 2 of that quantity, right? So yeah, that's it. This is the solution, right? um a way we can, let's just do this with an example. So let's take a give an example. The example is, let's just take the example of 0 0 0 0 0, right? So here count 0 0 is 4 and count 1 1 is 0. So we are saying that this should take exactly 2 steps. And why will it take 2 steps? Because what we can do is we can change this to a 1 and we can change this to a 1, right? We can change these two to 1, and now count 0 0 is 0 as well as count 1 1 is 0. So our answer is 2, right? And that's basically what we're saying, that how much ever the difference is, right? So count 0 0 is 4, count 1 1 was 0, so 4 minus 0 is 4. So our answer will be actually 4 by 2, right? Because each step we're increasing by 2, so it takes that much time to catch up, right? So this is our final solution. If we want to write this as a one liner, right? If we want to write this as a one liner, one liner, one liner with C++, we could write it something like this. We could write it as uh, count 0 0 minus count 1 1 by 2. So we want to take ceiling, right? Because we want to take ceil function, because that many steps we need. So we do like this and 0, right? So if you want a one line answer, we can just write this equation. You can prove to yourself that these two are the same thing. This is ensuring that the case where count 0 0 minus count 1 1 is negative, the answer becomes 0, right? So that's all. You can show that these two are the same thing, and we can write this in this one line solution. Time complexity, we just need to count 0 zeros and 1 1s. So the total time complexity is just big O of n, right? Time complexity is big O of n. Cool. Yeah. Let's have a look at the code. Okay. So we just take in n and the string s. We count the 0 0 and 1 1 in the string. So here we're doing that. And then finally we just print this one line answer. Count 0 0 minus count 1 1 plus 1 whole divided by 2 comma 0, right? Okay. So I'm assuming this is clear. Should we move on to the next question? Problem 3. Okay, so moving on to problem 3, distinct func. Yeah. So I found problem 3, to be honest, easier than problem 2, but I mean both were pretty easy. But yeah, today's contest was, I think, overall easier than usual. But okay. Problem 3. Given an array A of length n, in one operation we can choose a prefix of the array and apply bitwise XOR operations to all elements in the prefix. Okay, so we can choose any x and any prefix length k and apply a bitwise XOR to all of them. Okay. Your goal is to make the elements of the array pairwise distinct, or we need to basically make all the elements of the array distinct with the minimum number of operations, right? So with the minimum number of operations, we want to make all the array elements distinct. N goes up to 10 power 5, elements go up to 10 power 9. Note that on x there is no restriction. Okay, so here basically x can be as large as you want, right? So there's no restriction on it, and the prefix length is also k. Okay, so here there'll be some very simple ideas which we're going to use. So you need to know how XOR works, obviously. So yeah, let's just write down the expected time complexity. So obviously here the expected time complexity is going to be again big O of n or big O of n log n. right? And let's take this example. Okay, 0 1 0 1, right? And we want all the array elements to be distinct using the minimum number of operations. What is the operation we're given? Our operation is that we can pick any prefix and we can XOR it with the given element z, right? So if we choose a given prefix and we XOR it with the given element z, for example, if we choose some very large number like 10000, what happens? So basically, all these numbers get XORed with that, right? So they become something like this. Make sense? And basically every time, so basically our approach can be something like this. Basic intuition. When we go from right to left, when we scan elements from right to left, every time the current element has previously appeared, right? So we want to make sure the elements are distinct. So every time the current element has previously appeared, we can XOR this prefix. We can XOR this prefix with some value, right? With some value. So for example, this 1 is fine because it has not appeared so far. This 0 is fine because it's not appeared so far. But then as soon as this 1 appears, we will XOR this whole range, okay? So let's say we XOR this range with 2. And then what happens? We get 2 3 0 1, right? So now this is fine, this is fine, this is fine. Then we go here, 2 is also not appeared before, so the whole thing is fine. And our answer was 1 step, right? 1 step. Cool. Okay, and also what does XOR mean? XOR basically means that we're flipping some bit, right? So given z, when we XOR it, basically it means that we're flipping some bits of the first n numbers, correct? For the first k numbers, we can flip any bit. So our idea is going to be, key idea, whenever we are forced to do the XOR operation on some prefix, right? Whenever we are forced to do the XOR operation on some prefix, we can choose a very large z. We can choose a very large z because we can XOR with any number z greater than equal to 0, right? So we'll choose something like z is 1 0 0 0 0, like a lot of zeros, right? We can choose a very large 0, and basically what will happen is all the XORs will become distinct from that point onwards, right? So we can choose some very large z and make all the previous elements and make the whole prefix distinct. Make the whole prefix distinct for sure, right? Distinct for sure. So let me show you what I mean. So let's say we have 0 1 2 1 0 2 2 3 1 3 2 1 0. Okay, so what happens here is this 0 is fine, right? This 0 is fine, this 1 is fine, this 2 is also fine. Now this 1 is not distinct, right? This 1 is not distinct. So what we'll do is we'll take this whole prefix and XOR with some large z, okay, large z, and let's say it's like 1 0 0 0, okay, because for this array this is a large z. So assume we have XORed with that. So now this value will be like this, this value will be like this, this value will be like, basically we're writing it in bits, right? So this value is going to be something which looks like this, right? And so on, right? So basically there's a bunch of zeros and then the final, these values are repeating again. So basically by XORing by a large value, Since that large bit is going to be only set here, like large bit only set here and not set here, not set here, we have ensured that this XOR has made sure that this left half is distinct from the right half, right? We have made sure that this left half will always be distinct from the right half. And again, we can continue this process. So this will be distinct, this will be distinct, this is distinct, then this is non-distinct. So again, we will XOR with some very large number, right? So again, these will all be distinct. Now again, we start this process. So this is fine, fine, fine. Again, we take a very large number and XOR it, and then all of these will be distinct, right? So basically, our idea is go from right to left. Initially, answer will be 0, right? And we have an empty set. Empty set. If current element, so if a of I is in the set, that means that we XOR the whole prefix. So we can say that the whole prefix will now be different from the remaining numbers. So what we'll do is we can do answer plus plus because we used one operation, and we can do set dot clear, right? We can do set dot clear, and now we can add this number to the set. Okay, so we'll do set dot insert a of I, right? Because each time we need to do the XOR operation, we can make sure that the whole prefix becomes completely distinct by choosing a very large Z. That's our essential idea. And now finally, when we're done all this, we can just print the answer, right? So that's it. This is our whole idea. In my code, I used a map, but you can use set or unordered map, whatever you want. It doesn't matter because we just need to know how many times a of I appears. That's it, right? The best ideal way to do it would be use an unordered set. Okay. So is this clear? Will you explain counting MEX is fun? Yeah, I'm going to explain the first 5 problems. So I will be explaining that. Okay. Problem C understandable, guys. Let's have a look at the code. Yeah, third problem. Taking the elements, answer is 0. Instead of set, I'm using a map here, same thing. If the value is already in the map, we're going from n-1 to 0. Okay, so reverse order, right to left. If the element is already there in the map, we can increase the answer and clear the whole map. Basically, we're doing XOR operation to this point and making sure it's all different. Now we add this element to the map and we continue. We print the final answer. Right, so very standard greedy kind of idea. So does this make sense, guys? Just quickly tell me in the chat if it makes sense, and then if it does, we'll move on to the next question. If you use unordered map, the time complex will be big O of n. Since I'm using a map and it's an ordered data structure, the time complexity is big O of n log n. But that doesn't really matter. The n is fine for either solution. Right. Is this solution fine, guys? Any doubts? Okay, no doubt. So let's move on to the next solution, I guess. Interesting binary, easy version. So I guess most people solve three questions. So fourth and fifth, I guess you should pay attention. Okay. Given an array A of length n, each element is either 0 or 1. We can increase any element by 1 and perform such operations any number of times. Okay. So basically, we want to make the array adjacent distinct. That is, a of I should not be equal to a of I plus 1 for all I. Find the minimum number of operations to do so. Each element is initially 0 or 1, and our operation is to add by 1, right? So the only operation we are given is add by 1. That is the only operation we can do, right? And here's some examples. So if we have 0 0, it needs one operation, right? So let's get in here. Problem 4. So if you take the example of 0 0, Then since 0 is equal to 0, what we can do is we can increase this by 1, right? We can do operation on this, and this becomes 0 1, which is adjacent distinct, so the answer is equal to 1. Okay, another example, let's take the example 0 1 0 0 1 1. So 0 0 1 1. Now here we have 0 0, so we'll make this 0 1, and now we have another 1, so we'll make this 2 and 1. Okay, so this will take 1, this will take 1, so our answer is going to be equal to 2, right? And that's about it. What is the time given for this? So n goes up to 2 times 10 power 5, right? N is less than 2 times 10 power 5. So the expected time complexity is going to be big O of n or big O of n log n, right? Okay, so this is a very standard kind of problem. If you're stuck in it, you would maybe not get this idea, but it is a pretty standard problem. And the first and main thing you have to observe is, let's take a big example. Okay, let's take a big example. Let's say the example is 1 0 0 1 1 1 0 1 0 1 1 1 0 0. Okay, this is a big example. Now let's say we do a very greedy kind of solution, like we have 1 over here. Now this 0 is fine. Now this 0 does not want to be equal to the previous one, so we'll make this a 1. Right? This 1 does not want to be equal here, so we'll make this a 2. Now same here. So now this is not equal, so this is 2, this is 1, so it's fine. Similarly, again this becomes a 2, this is a 0, and this remains a 1, this remains a 0, this remains a 1, this becomes a 2, this becomes a 1, 0 1, right? So this is one possible solution to this. And basically the main observation, as you can see here, is that since the array consists only of zeros and ones, to make sure that no adjacent elements are distinct, largest possible answer which we can have, largest possible value of our final array is 2. Okay, basically I'm trying to say that all the elements will be within 0 1 or 2. Okay, each element in our final answer is going to be either 0 1 or 2. And why is it either 0 1 or 2? Basically, let's take the case where we have a 0 0 adjacent, right? So if we have a 0 0 and the next element is 0, then all we need to do is okay, let me just give you an example. Let's say we have 0 0 0, right? So to avoid the adjacent elements to be equal, we can make it as 0 1 0. And what if we have a 0 0 1, right? So to avoid adjacent elements to be equal, again we can make it something like 0 1 2, right? And then if we have 1 1 1, we can just make it 1 2 1, right? In no case do we ever need to make a 3. Never do we need to make a 3, right? So we never need to make a 3, right? So each possible element is at each element is either a 0 1 or 2 for our final answer, right? Each element is either a 0 1 or 2 for a final answer. So I hope this is giving you ideas. So I hope this is giving you ideas, because the observation we can make from this is very simple. We can say that for each I, we can have a dp of I 0 1 2, right? So for each I, if the value at this position was 0, right? So we can call this dp of I 0. And if the value at this position was 1, we can call this dp of I 1, right? dp of I 1. And if if the value was 2, we can call this dp of I2. Okay, or if you want to look at it from the other perspective, we can say that the last element is either 0, 1 or 2, right? The last element of our answer is 0, 1 or 2, right? Then if it is a 0 or it's a 1 or it's a 2, now from the last element again we have two cases. The second last element is either 1 or 2 if it was this case, and then in this case it is the second last element is either 0 or 2, and in this case either it's 0 or 1, right? And so on. So basically for each element we have this kind of recursive structure for our dp, right? We have a recursive structure for our dp, for the second last element, for the third last element, and so on. So basically that's why we can make a dp table on it, right? So basically our dp of I is going to be the cost to make it equal to this value. So like for the last element, so for the last element it's going to be like the cost to make this value equal to 0, or the cost to make this value equal to 1, the cost to make this value equal to 2, plus the minimum of these two cases, right? We want to find the minimum, so the previous two cases will take the minimum. Okay, so let's just formulate our dp now. So let's just cleanly formulate our dp formulation, right? What is dp of ij? Okay, so dp of ij is going to be, so j will obviously be less than equal to 2, I will be less than n, and is going to be basically the minimum answer for adjacent unequal, minimum answer for adjacent unequal position I has value equal to j. Okay, has value equal to j, right? And what will be our transition for this dp? What will be the transition? Basically it will be the cost to make position I equal to j, right? So how many times we need to add to make it equal to j? So dp of I comma j will be the cost to make position I equal to j. So for example, if position I was originally 0 and now j is equal to 2, then the cost will be equal to 2. Similarly, if position I was initially 1 and now j is equal to 2, so the cost will be equal to 1, right? And what if originally the position I was equal to 1, right? What if position I was equal to 1 and j is equal to 0? So in this case it's impossible, right? In case it is impossible, because we can only add a number, we can't decrease a number. So in this case we will say the cost is infinity. Okay, in this case we can say the cost is infinity. Fine. So the cost to make position I equal to j, plus now the two options, right? So for k not equal to j, for k in we need to take minimum, right? So we want minimum cost. So minimum for k not equal to j, because we don't want the previous two to be equal, dp of I minus 1 k, right? So this is going to be a transition, right? And because j is 0, 1, 2, k is 0, 1, 2, our total time taken, total operations to compute this dp is big O of n times 3 times 3, is again big O of n itself, right? So that's it. We can have a simple dp big O of n times 3 dp, and we just need, for each element we need to consider 0, 1, 2 as the possible cases, right? And memory will be simply big O of n times 3, right? Right, that's it. What is our final answer? Our final answer will be whatever is the minimum of dp of n minus 1. So n minus 1 can be either 0, 1, 2, we don't care. So it will be the minimum of these, right? So this is our final answer. Okay, so that's about it for this problem. As soon as we implement this dp, we get our answer. So let's have a look at the code for this. If you want to know why we are not doing greedy and why we're doing DP, it's because sometimes making a value equal to 2 instead of a 1 might be more helpful, or things like that, right? So since there's only three possible values, 0, 1, 2, we might as well just DP it directly, right? There's only three cases. Each case depend on the previous case, and they are overlapping sub problems. So that's why we're doing a DP. Very standard kind of DP idea. Okay. So let's have a look at the code for this. So we have an array A. We are taking input of that. We have a DP of n cross 3, right? N cross 3. We are filling it with infinity, right? So int max by 10. So this is my infinity. Why am I filling by infinity? Because initially I'm considering the case as impossible unless it's possible, right? I'm defining a cost function. What did I say for the cost? So if we have to make a of I equal to j, right? So if a of I has to be equal to j, but if a of I is already greater than the value, then you cannot make it equal. So in that case, we just return infinity. Otherwise, we can return the number of steps taken. So that's simply x minus a of I, right? So that's the cost function. Now we're doing the base case. So obviously for 0, all three cases are possible. So we just put dp of 0, 0 is cost of making the 0th element 0. dp of 0, 1 is the cost of making the 0th element equal to 1. dp of 0, 2 is the cost of making the 0th element equal to 2, right? So that's it. Now for every I, for every j, and for every k not equal to j, right, we are doing the update. So dp of ij is the minimum of dp of ij, and dp of I k minus 1 plus the cost of making the ith element into j, right? So dp of I minus 1 k plus the cost of making the ith element into j. Finally, we can print the minimum of all the three possible values for the last answer, right? So that's it, standard DP. If you had trouble with this, I guess you probably need a bit more practice with these kinds of DPs. But yeah, is the solution understandable, guys? Is odd even subarray size used in this question? No, it's not. It's not. I don't see why it is. Atul, so the self-paced courses, the lectures are pre-recorded. Although we do have earlier used to have live classes, and maybe in the future we might have live classes, but currently the self-paced courses are pre-recorded. Yeah, the thing about greedy is, right, you cannot depend on local minima, because the issue is that sometimes you want to make an element 2, instead of 1, or you want to make an element 0 or something like that, and later on it helps you. So that's why the DP is used here, right? And since there's only three values, 0, 1, 2, I think the DP should strike your mind quickly. Nothing much to think about. Okay, so let's move on to the next problem now. Problem D, you can see. But yeah, the ideas going into this is pretty nice. Okay, so final problem for today, problem 5, or problem 5 of the contest. Okay, counting MEX is fun. So yeah, this took some time for me as well. I took almost an hour on this, but to be honest, that was my mistake. The problem was pretty simple. Okay, for a given sequence B, the MEX of the value of B is denoted as MEX of B is the minimum excluded value, right? So the smallest non-negative integer that does not appear in B. So if you have done enough CP problems, you know what MEX is. So I won't bother explaining too much. Given two integers n and k, consider all permutation from 0, 1 till n minus 1. Define a set P as containing all distinct MEX value of its subarrays. Okay. So S of P is the distinct MEX values of all of its subarrays. Okay. So our task is to count how many permutations satisfy S of P. The cardinality of S of P is equal to K. All right. So the size of S of P is equal to exactly K. How many permutations are there such that that's true? Since the answer is large, find it modulo 10 power 9 plus 7. That's fine. Observe the constraints. So n and k go up to 5000. Okay, so n and k go up to 5000. So big O of n squared, big O of m times k solutions are possible. Okay, so just let's write this down. Expected time complexity. we can have n squared, but we can't have n cubed solutions. We can have n squared log n. That's perfectly fine for these constraints. Okay, so how do we even approach this problem, right? Let's try to get our bearings. Let's try some examples because it's not very obvious what even it's asking. So basically what it's saying is count how many permutations of length n have exactly k possible MEXs by choosing its subarrays. Okay, choosing its subarrays. K means distinct k, obviously. K distinct possible MEXs by choosing its subarrays. So let's take an example and figure out what this means. So let's say our length is 3. Okay, length is 3. So what are the possible permutations? We have 0, 1, 2. We have 0, 2, 1. We have 1, 0, 2. We have 1, 2, 0. Right? So there are many different permutations possible. And we have 2, 0, 1, 2, 1, 0. Right? All these different permutations are there. And what we're going to do is consider the MEX of the subarrays. Okay, so first off, if we take MEX of this much subarray, right? So the MEX is 1. And if we take MEX of this much, the MEX is 2. And if we take MEX of this much, the MEX is 3, right? And if we take MEX of this much, its MEX is 0. So as you can see, 4 total possible MEX are there, right? 0, 1, 2, 4. Sorry, 1, 2, 3. These are the possible MEX. So the answer for this is 4, right? So we can say that this has 4 possible MEX. So this is one permutation which has 4 possible MEX. Similarly, since this is just the reverse of that, we can say this is also 4, right? This is also 4. Now let's try to see this one. MEX of this is 1. Let's say MEX of this is 0. MEX of the whole thing is 3. MEX of these two is 1. MEX of these two is 3, right? So basically 3 are possible here, right? 3 are possible here. Similarly, you get different counts, right? So basically we need to tell for a given value of k, how many such permutations will satisfy it. So let's try this one as well. So here 0, 0, 1, 2, and so on. So this will be 4. This will be 3 again because the opposite of this. And this will also be 4, right? So basically for n equals 3, k equals 4, answer is going to be 1, 2, 3, 4, right? So answer will be 4 here. For n equals 3, k equals 3. There are 2 ways, right? 2 permutations. So the answer is going to be 2. For n equals 3, k equals 2. Answer is 0. N equals 3, k equals 1. Answer is again 0. Right? Makes sense? So this is what the question is asking. Given an n and k, how many different permutations have exactly these many distinct MEX in their subarrays? Right? As exactly these many distinct MES in their subarrays. Okay. So now how do we approach this kind of a problem? So directly counting, if you try to directly count, like I tried to directly count, it becomes pretty hard to understand how to exactly count these because the permutations can be arranged in so many ways and there are a lot of issues which arise, right? Instead we're going to look at an interesting thing which happens. So after some playing around, you might come across this observation. So let's get into observations itself because these things take some practice and some intuition. So observation / intuition, which is going to be a spark of inspiration for this problem. Okay, so I'll tell you what the interesting thing which happens when you play around with these is, let's say there is some right. So let's say there is some n equals, let's say 6 elements, right? N equals 6 elements here. and it has some answer k, right? It has some k different possible MEX. Okay, let's say it has some k different possible MEX. Okay, so it has n equals 6 elements. Let's say there's some k different possible MEX, and now I want to know if I add another element, if I make it n equals 7, right? If I make it n equals 7 and I add a 6 to this, what happens to my k? Okay, how many different possible MEX are there now? Fine. So basically, um, let me take a simpler example so it's more easy to understand. So let's just take example 0, 1, 2, 3, 4, 5. Okay. Okay. So basically, if I add my 6 at the end, okay, if I add my 6 at the end, let's just write down the possible MEX. So the MEX still here is 1, MEX still here is 2, 3, so on, right? So I'll just write it down over here. So MEX is 1, 2, 3, 4, 5, 6, right? So if I add a 6 at the end to this array, my array will look something like this, right? I added a 6 at the end. So now I get a new possible MEX, right? So my k has increased. K has become one more because now there is a new possible MEX. Now there is a new possible MEX of 7. Okay, or we can say that the number of possible MEX has increased by 1. Correct? The number of possible MEX has increased by 1 if I added a 6 at the end. Okay, so far so good. Now, what if instead of adding a 6 at the end, I added a 6 somewhere at the middle over here? Okay, I added a new, my next number I added somewhere in the middle over here. Now, what happens? So, I added a 6 here, and let's say, what was the number? 5, sorry, 4, 5, right? Something like this. Okay. Now, if you see, now again, 0 is important because the subarrays including 0 itself will have larger MEX. If 0 is not included, then it will always be 0 itself, right? MEX will be 0. So that's why we're checking subarrays which include the 0, right? So keep that in mind. We're checking subarrays which are including the 0 only. Now if I take MEX up to 3, again it's the same. But if I take MEX over here from 0 to 6, this MEX will also be 4, since 4 is the smallest missing number, right? The 4 will be the smallest missing number. So the array looks like 1, 2, 3, 4, 4. Now here it becomes 5, and here it jumps to 7, right? So as you can see, we completely skipped over 6. We had 4, 4, then 5, then 7, right? So we completely skipped one number, right? So in this case, k stays the same. K stays the same. Okay. So basically what we're doing is we're adding a 6 to make it go from n equals 6 to n equals 7, and we're adding the 6 in the middle over here. Okay. And the previous case, we added the 6 to the end. Okay, we added the 6 to the end. Right, and let's just list down the possible MEXs for this also. So we can have like a comparison. The comparison here will be 1, 2, 3, 4, 5, 6, 7, right? Now here k plus equal to 1. As you can see, if k possible MEX were there earlier, now it has increased by 1 because this 7 is a new possible MEX. Meanwhile, if 6 was somewhere in between the original elements, the old elements, what happens is that we have 1, 2, 3, 4. 4 gets repeated because this element is missing, right? So the larger element has come in between the smaller elements. So the MEX does not increase. And then the total k possible MEX remains the same. Okay. And we can see that even if the array is not neat like 0, 1, 2, 3, 5, you will see that this is still true. Okay. So if we have, let's say, 1, 2, 0, 4, 5, right? And 3. If we add a 6 at the end, then we will have a new possible MEX of 7, right? But if we add a 6 somewhere in between, the MEX, the number of possible MEX does not change. Okay, possible MEX will not change, because basically what's happening is all the MEX from this point onward, they need, for example, the MEX which includes 6 is going to include 2 also, and it's going to be missing a 1. So basically the 6 is getting included before a smaller number, right? So larger number we added is getting included before the smaller number is getting included, right? Getting included before the smaller number. So this is the rough intuition for why this is happening. before the smaller number. So it's not affecting the total number of MEX. So it's not affecting distinct count of MEXs, right? So basically, if you add the 6 in the middle, it does not it does not change. If you add the 6 at the ends, it will change. Similarly, if you added the 6 at this end, right? If you added the 6 at the start, then also it would change, right? So basically, for a given permutation of n elements, l elements, whose count of distinct MEX is k, if we add element to make its size n plus 1, to make its size n plus 1, if we add at the end, so there are two ways to add at the ends, right? So if we have the following values like this, then there are two ways to add at the end. We can add it here or we can add it here, right? And to add it in the middle, we have these many positions, right? To add it in the middle, we have these many positions. So basically, we're going from n minus 1 to n. So we can say that two ways to do this and n minus 2 ways to do this, right? Two ways to add at the ends and n minus 2 ways to add at the sides, sides, right? So that's basically what we're saying. So n minus 2 ways to add in between, and these two ways to add at the ends, right? So, okay, so what conclusion is this giving us? So again, we can have like a dp value, right? Dp idea again. If we want the count for dp nk, right, it has to have come from n minus 1k, because the largest element n must have been added at some position, right? So it must have come from n minus 1. So what we can say is either it was added at the ends or it was added in between, right? If it was added at the ends, the k has increased. So that happens in two ways, right? So that will be dp of n minus 1 k minus 1. Or if it was added in between, that can happen in n minus 2 ways. That can happen in n minus 2 ways, and that could only happen from n minus 1 k, right? That could only happen from n minus 1 k, right? So basically what intuition we had was, if you already have the answer for n, how do we find the answer for n plus 1? And basically when we're trying to find answer for size n plus 1, we realize that this n plus 1th element needs to go somewhere. If it goes in the sides, k increases. If it goes in between, k remains the same. So based on this idea, we come up with this dp logic, right? And this is a kind of familiar dp idea for me also, but it did take time to come up with, especially if you start thinking in terms of combinatorics and get lost in some rabbit hole. So yeah, so a dp idea. Okay, what about the base case? When does this hold true? So this holds true only if you have this holds true if you have at least n greater than equal to 2, right? Because when n is equal to 1, there is no meaning of adding in the between. There's no meaning of adding in between, right? There's no meaning of adding in between. So basically we need to hold our base case, which we need to handle, our dp of 1 1, dp of 2 0, dp of 2 1, dp of 2 2, and dp of 2 3, right? So these are the base cases which we need to handle in our dp, and most of these will be zero itself. So there are very few base cases. And then for n greater than equal to 3, because each is derived from the previous n by adding the largest element in between or at the sides, right? And we already showed if you add in between, this happens. If you add at the sides, this happens. There are two ways to add at the sides. There are n minus 2 ways to add in between, right? So that's why this is our formula using basic combinatorics, right? Okay, now to handle the base cases, most of the base cases already given for us. dp11 is 1, and dp12 is obviously not possible since there's only one permutation, right? Similarly, dp21 and 22 are 0, so let's not care about that. only possible answer is dp of 2 3. Dp of 2 3 is 2. So dp of 2 3 is 2, right? So these are our base cases. This is our dp transition, and our final answer is simply dp of nk. Final answer is simply dp of nk, right? Dp table size, what is the dp table size of memory, right? Dp table size, that will be n plus 1, because we need n elements, times n plus 2, because k can go up to n plus 1. So this will be our dp, right? Our dp array will look something like int dp of n plus 1 n plus 2, right? Something like this, right? This will be our dp array. And what else? Because for each test case we can't do this, right? Because there are 1000 test case, but since n and k are only up to 5000 each, then what we can do is simply pre-compute all the dp values in the table, pre-compute the whole dp table and store it, right? The whole dp table and store it, right? Then just answer all the test cases. Then just answer all the test cases, since this dp table is not very large, right? And make sure to use modulo the whole time, because obviously that will be needed. Okay, so let's have a look at the code. Here we're just defining the value of mod. As you can see, each test case we just take in n and k and see out dp of n and k, because we pre-computed it. Our maximum n is 5000, so that's what we have here. Our dp table is n plus 1 times n plus 2 size. We fill it with all zeros in the start. Here are our two base cases. So dp of 1 1 is 1, dp of 2 3 is 2. So that you can do by hand, or you can just read the example. They have explained why. 1 1 is 1, and for 2 there are only two possible answers. So this is for 2, right? And you can verify for 3 that this formula works, right? So for 3 we already calculated here. And if you check this formula out, you'll see that it's working. And yeah, the formula, once you realize the formula is pretty simple, right? Because each n must have come from n minus 1, and n minus 1 had two possible ways in the ends, and which increase the value, and the ways in the middle don't increase the value. Okay, so what else? We are going through the code, right? So for I equals 3 less than n, for j equals 1 less than I plus 1, we are filling all the dp tables. Make sure to use long while doing this multiplication and addition, because it might become bigger than int before you take the mod. So yeah, just the addition, the multiplication parts, we convert it to long, we do percent mod, and then we convert it back to int. Right, that's about it. The code is pretty short and sweet for this, although the formula might take some time to come up with, right? Okay, any doubts, guys? What is the time complexity? The time complexity is just n squared, right, for pre-compute, and t to pin the test cases. So time complexity is just big O of n squared plus t. All right. Okay. So now this brings us to the end of the session. Any doubts, guys? Yeah, so focus, your ideas are pretty greedy kind of ideas, right? Like you're making some observations about the MEX, and yeah, those observations are nice, but they don't help us coming up the DP solution. The DP solution is very general and it handles a lot of things. But your ideas are right. Okay, any general doubts, guys? Any doubts regarding the questions, or any general doubts? Doubts. Any general CP related doubts if you have? Also, yes, forgot to mention, but if you aren't already aware about it, we at TLE Eliminators have self-paced competitive programming courses, which are live right now on our website, tle-eliminators.com/courses, right? So go ahead and check them out. These courses are at 4 different levels. So they take you from the very beginning of coding, space and time complexity searching, C++, strings, all that, to the very expert level, dynamic programming, trees, graphs, DSU, right? Segment trees. All of these courses are super affordable. So like they range from like 1K to like 4K. So not much investment compared to the returns you're getting. Each course is giving you more than 40 hours of recorded lectures, more than 100 plus practice problems, hints, video solutions, doubt support, right? So for all this only for such an affordable price. So definitely do check it out, guys. Also, the doubt support is very helpful because you get high rated coders. Most of them are expert, at least, to just pick your doubts. If you have any, you make a new doubt on Discord and they pick it up and they answer you. So it's a pretty useful course. Do check it out. Cool. Okay, looks like no doubts today. And yeah, to be honest, it was a pretty simple contest. So if you're getting stuck with any part, definitely do rewatch the part, because I can get maybe the last question, the DP was a bit confusing, but do check out the intuition. Do like you need to write down the cases yourself and see that this works, right? Like write down a few cases, try to see how to convert n to n+1. You'll quickly catch on, I think. Right? Okay. So that brings us to the end of this session. Thanks everyone for watching, and see you in the next PCD. Bye bye.